Hey guys, this is going to be my video on section 6.5 from our textbook dealing with the graphs of polynomial functions. In 6.4, we talked about kind of what the graphs would look like. Today, I'm going to show you how to graph them by hand, how to use our calculator to graph them, and then some common things we look for in the graphs of polynomial functions, especially when they are greater than just x squared or x, linear or quadratic. So by hand, the first thing we need to know is when we're making a graph of a polynomial, you can never go wrong with making a table. Now, right here, f of x equals x cubed minus 4x squared plus 5. Before I start making the table, there is something important that you want to realize. And that is, what is this graph going to look like? Because we need to know when we can stop our table. I'm going to give the example, if you remember, absolute value functions always look like a V for value. And so we knew we could stop plugging in points once we found that rebound point, it going up, going down. We want to know what this function looks like so we know when to stop plugging in points. So from 6.4, we know this is a positive leading coefficient and an odd degree function because the x cubed. This should look something along the lines of 1, 2, 3. We should go up and then down and then up. And so we want to be able to find that shape when we plug in points. Now I say by hand, but what I'm actually going to do here is just start plugging values into the function using my calculator. A little bit quicker, oftentimes more accurate. I'm going to say -2 store in x, and then I'm going to type out my function. X cubed minus 4x, got to get out of that exponent. X cubed minus 4x squared plus 5. And so it says -2. When we plug -2 in, we should get -19. That's way down below. What if I plug -1 in? -1 store in x, then I'm going to use that second enter. Hit it twice to get the second most recent command I've typed in. -1 gets us 0, looks like. So it definitely went up. So here's where I think we are. We were way down, we're going up. Let's keep plugging in values and seeing what we get. So if I plug in 0, probably don't even need to use the calculator for this one. Plug in 0 into our function, we get 5. Okay, so we're still going up. If we plug 1 into our function, 1 store in x, we get 2. Now, if this were like a parabola or something, we would have found the shape. It went up and now we're going down. We're back down to 2, but we know there's a whole nother part we need to look at. So let's do a couple more. 2 store x, we got to find where does this thing start its upturn. Not there. 2 is at -3. What about 3? If I plug 3 in, I get -4, still going down. If I plug 4 in, I'm all the way back up to 5. And so I was going down, 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 and then I started going back up again. And now I know I have the full shape of this graph, if you will. I know that it needed to go up, down, up, and I found some points that illustrated that. So let me put those on the graph. -2, -19. I'm not really going to put that one. That's way down there. So I'll just know that it came from way down there. I also have -1, 0. That'll be my arrow in a second. 0, 5, 1, 2, 2, -3, 3, -4, and 4, 5. And so we can kind of see the shape of this graph start to take form. It's just a sketch, but looking something along those lines, up, then down, then up. So as far as graphing polynomials, tables are often where we're going to go. We're plugging in points, we're looking for the shape of that polynomial. I do want to show you and remind you how we can use the calculator to make this process even easier though. Instead of plugging things in one by one, I'm going to go up to y equals, and I'm going to plug in my function, x cubed minus 4x squared plus 5, hit graph. And it looks pretty similar to what we have, right? Theirs is obviously nicer. It's on the calculator. It's drawn out more smoothly. But the shape is basically the same. Now, here's where it can really go quickly. If we hit second and then hit the graph button again, the second functionality of the graph button is a table. And if you look, it actually just grabs those points for you. It makes that table for you. So when you're graphing these polynomials, I am totally okay with you plugging it into your calculator, finding this table, and kind of writing down those points. Again, we need as many as we need to find the shape of the graph, but we can go up or we can go down in our table and see, okay, so it's going up, now it's going down, now it's going up, and it looks like it's going up forevermore to really high numbers. So don't be afraid to utilize your calculator for that. Couple things that we often look for on graphs. The first one is zeros, roots, solutions. We spent so much time in chapter 5 talking about those. We want to look for a zero. And one thing that comes into play a lot of times is something called the location principle. And here's what it says. If we plug in some x value, and let's say we get a value below the x-axis, like the one I just circled, and then we plug in another x value and we get something above the x-axis, what the location principle says is somewhere in between those 2 points, A and B, that we plugged in, we must have crossed the x-axis. There's no way to get from below to above in a polynomial function without crossing the x-axis. So somewhere in between there had to be a zero where we hit the x-axis. Now it's kind of an intuitive result, you might say, but it's one that we're going to use, and we kind of need to just formalize and make sure everyone agrees. Okay, if we started below, ended above, we must have crossed it somewhere in between. Same thing if we started above, ended below, we must have crossed it somewhere in between. So zeros are going to be something we're looking for. The other points on a graph that are oftentimes most interesting to us are the relative extrema. Now, the relative extrema are the relative maximums and the relative minimums. So a relative maximum is nothing more than the top of a hill. It's not the absolute maximum, because if you're looking at this graph on the screen, it goes up forever on that left-hand side. So there is no absolute maximum, but there is a relative maximum, a point that's higher than all the other ones in the region. So relative maximums are the hills. Relative minimums are the valleys. That lowest point, whenever we have a valley, that is a relative minimum. So when we talk about these, the highest or lowest points, the max and the min are generally the y values, because we're saying, what is the maximum y value we get to? How high did we get? What is the the minimum y value we got to? How low did we get? And those are maxes and mins. We also oftentimes speak of where are they? Where did they occur on the graph? And I'm going to demonstrate that right now. So right here, I want to know, are there any relative mins? Are there any relative maxes on this graph? I'll start with the relative mins. Yes, there's definitely a bottom, a valley, if you will. And I'm going to say that this point is probably like -2, -1.7, maybe. That's kind of an approximation. I don't have an exact answer, but it's definitely past half, not quite to, made one quick mistake, -0.7. How about? It's not quite to -1, but it's more than halfway there. So I just said -2 and then -0.7. So what is the relative min? We would say that the relative min equals -0.7. and that it occurs at x equals -2. So the occurs at is the x coordinate, the min is the y coordinate. Same game, let's play it with the maximums. Are there any relative maximums? The answer is yes. There's one right here, there's another one right here. This guy looks about -3, 0.8. This one looks at about 0, 1.9, not quite all the way up to 2, but not far away at all. So what would I say for my relative maxes? I would say relative max, yep, there are 2 of them. One of them equals 0.8, and that's at x equals -3. The other one is at 1.9, and that happened at about x equals 0. So relative maxes, relative mins, just saying what are the highest points in the region, the lowest points in the region, those hills and those valleys. And we're taking the y coordinate, and if we're asked where it occurs, we use the x coordinate. Okay, so we're going to put all that together in one more problem, and then that'll be it for this video. It says make a table to graph f of x equals -x cubed plus x squared plus x minus 2. Estimate the relative extrema, locations of the relative extrema, and the zeros. So let's do this. I'm going to use that calculator and just use it to find the table for me. So I'm going to go on, I'm going to say y equals and clear that out and get -x cubed plus x squared plus x minus 2. Type it in, hit graph. It should be kind of a downwards facing cubic, so down, up, down, which it looks good. Then I'm going to go second table. And sure enough, here's a bunch of beautiful points. So I'll start making my graph over here, x, y. I'll say start at -2 because that looks like kind of where the action started. And we get 8, -1, -2, -1, followed by -4, -17, so -4, -17, and -46. Let's see what shape that gets us. -2, 8. 6, 7, 8 is like way up here. -1, -1, 0, -2, 1, -1, 2, -4, and then the other ones are just so far down there, I'm not even going to really include them other than to say, look, we're going down there. Not the prettiest graph ever, but it works for a sketch. Remember, that's all this is. So it says estimate the relative extrema. Well, let's start here with my relative min. I'm going to say that this has a relative min. The relative min is -2, and it happens at about x equals 0, roughly. Again, this was just a sketch, but it happens at roughly x equals 0. There does appear to be a relative max somewhere around this. So I'm going to say equals about -1 at x equals 1. Just the hills and the valleys. And then lastly, what is an approximation for my 0? A little bit less than -1. So I'm going to say my 0 is like -1.2-ish. I'll say x equals about, kind of squiggly marks, -1.2. Now I'm technically done with this problem. I estimated those relative extrema, those extreme values, the maxes and mins, where they occurred, and the zeros. Great. But I want to show you, just to wrap up this lesson, how to find those exact values on a calculator. It's really not hard. Here we have our graph that I typed in. Let's start with the relative min. I'm going to go to second calc, because I'm wanting to go to that calculate menu. And you see all my options there. Calculate a zero, that'll come in handy later, but I think calculate a minimum is what I want. Now, all three of these that I'm showing you today all follow the same pattern on the calculator. We go down, I'm going to hit enter to calculate the minimum. And it says, give me a left bound, a left boundary. So I'm going to move my cursor, my blinking little dot, just to the left of where it looks like there's my relative min. Then it says, give me a right bound. It's just asking us to narrow down the area it has to search. So I'll move my cursor to the right of that little relative min, hit enter. It asks me to guess, so I'll move my dot kind of around there. And it says the relative min is actually negative 2.1852 just about. We said it was negative 2. Turns out it's negative 2.1852. So pretty close with our approximation, but if you want to use the calculator, go for it. Notice that it's also at negative 1/3 for that x value. So I'm going to grab blue and say it's actually negative 2.1852, and it occurs at x equals negative 0.3. Repeating. Which again was pretty close to our approximation. I don't feel too bad about that. Just for an estimate. Let's try the max. So I'm going to go second, calculate. This time select, I want to calculate the maximum value. It says give me a left boundary, so I'm going to move it a little bit to the left of where I see that relative max. A right boundary, I'm going to move it a little bit to the right of where I see that relative max. Hit enter. It asks me to guess. I'm going to put it right about where I think it is. Hit enter. And it says the maximum is negative 1. And it happened at x equals 1. There's a little bit of rounding error with our calculator, but it looks like we nailed that one. Relative max was negative 1 at x equals 1. So our estimate was right on there from our sketched graph. Okay, last one, 0. Exact same thing. I'm going to go second, calculate a 0. It says move the cursor to the left of the 0. So give me a left boundary. I'll just move it right about there, a little bit to the left of where I see it. Move it a little bit to the right. There I go. Give it a guess. And it says negative 1.205569. And we had said about negative 1.2. So we were, again, just about dead on. Negative 1.2056, I'll say. Negative, need red. Negative 1.2056-ish. So, guys, we can use these calculators for a lot of different things, and it is worth it to become comfortable with them. They make our work more accurate. They make our work quicker and easier. On an SAT or something, if you're allowed to have these calculators, you can solve problems pretty quickly if you're familiar with how to use them. But whether or not you're there yet, or you're still just graphing these polynomials by hand, either way is okay. We look and we say, we know what the shape should be. We make a table of that many points until we can see the shape that we know we're looking for. Sometimes it'll ask us to find the relative extrema, the maxes and mins, or the zeros on this graph. And so this final problem kind of demonstrated all of that. So guys, that's 6.5. I'm hoping it makes sense. As always, if you have questions, write them down so you can bring them to my attention next time we meet. But that is all for this video. I will see you next time.